That's a fair old task you just said. Right, we'll make this thing work. I think now the microphone is off. I don't think it makes any difference to what you hear. I think it's for recording purposes. Well, I certainly am going to start at the beginning and talk about the theory of deformation quantization, because that's absolutely at the heart of all this. I've spent some time recently looking at Koncevich's papers. I think that's a good thing to do. But one of the things I found in these papers is that in his paper, the paper where he writes his what he regards as his definitive account, the first two references are to Bayern, Flato, Fronsdal, Lichnerowicz, and Sternheimer, who are the originators of deformation quantization. And the second, that paper, by the way, I checked on Google Citations, has 1,614 citations. So it really did start something. The second paper is a paper by Boardman and Vogt. Well, it's the book by Boardman and Vogt, Homotopy, Everything H-Spaces. And I certainly did not imagine some years ago that I would ever find a paper which another paper which combined work from both those two things. Such is the breadth, such is the sort of extraordinary variety and breadth of what Koncevich does. So I'm going to set up the problem first of all. Let's see. So set up the problem. Oh, can I turn that off, or does it make a difference? Does it make a difference, by the way? With I can. Okay, so after that little battle with technology, so I'm going to tell you about deformation quantization. Oops. I'm getting through the chalk pretty quickly. Go on. There won't be enough for your talk if I carry on. So deformation quantization. Now, this is, I should say straight away, that this is quantization as understood in symplectic geometry. With an S, you want a Z? With an S.
This is where we are.
This is quantization as understood by people who do symplectic geometry. So it's, I mean, of course, the original paper which I referred to is written from a physics point of view, but most of this is written from the point of view, most of this is studied from the point of view of symplectic geometry. And we start off with a Poisson manifold. Now, what this means is that it's going to be a smooth manifold, of course, but in addition, we've got the smooth functions on M, which I'll immediately call A, has got extra algebraic structure. It comes equipped with a Poisson bracket. So this is a bilinear function from A cross A into A, and it's normally written F, G goes to the Poisson bracket of F and G. And this is all we need to retain about it, is that it has certain convenient algebraic properties. First of all, the first thing is that the bracket is skew-symmetric. Oops. The second is it satisfies the Jacobi identity, which I'll write by saying that the bracket is a derivation of itself. Plus F, oh God, these curly brackets, G, H. So that says the bracket is a derivation of itself.
No, G.
Pardon?
F and G.
Oh, sorry, I beg your pardon. I haven't said it's a F, G, H. Yeah, sorry, I beg your pardon. Yeah, sorry. Yeah. Oh, I don't think, what?
Just switch F and G.
Yeah, sorry, thank you. That took a long time. Sorry, it's sometimes very difficult to see what you've written on the board, actually. And the third is that the bracket is a derivation of the product. So that's the Poisson identity. So, of course, there's the notion of a Poisson algebra. Which is just an algebra with a Poisson bracket which satisfies those algebraic identities. And generally, everything I say will be valid for a Poisson algebra. Now, it follows that in our symplectic situation, that this thing, I just will not move. It follows because in the symplectic situation, this bracket is given by the Poisson tensor, P. Sorry, I haven't done. P, this is the Poisson tensor. It's a section of M of the second exterior power of the tangent bundle of M. God, I'm really destroying the chalk at a fantastic rate. It's a section of the second exterior power of the cotangent, of the tangent bundle. Notice this is the tangent bundle, not the cotangent bundle. I'm not talking about a two form. I'm talking about what you'd call a two vector field, polyvector field. And this is really gives the relation. This really tells you how a symplectic manifold has a Poisson structure, has a natural Poisson structure. The symplectic manifold comes with an element omega in the sections M, the second exterior power of the cotangent bundle. Now this form is meant to be non-degenerate. In other words, it identifies the cotangent bundle with its dual. So in particular, it identifies these two things. And the Poisson tensor associated to a symplectic structure is just the element in this space of sections, which comes from this, using the isomorphism of these two things defined by the symplectic form. So that's the Poisson tensor. And its relation to the Poisson bracket is that the Poisson bracket of F and G is just P, the Poisson tensor, applied to dF wedge dg. Okay, so associated with this symplectic structure, you have the Poisson tensor. That's important because it's going to play a role in what I have to say later. Now, the next thing to say is what I mean by a deformation quantization. Now, for this, I need the notion of a star product. Sorry, I'm going to do. I'm going to. Okay, I'm going to go like that. So, a star product so if this thing is a product on not A, not the algebra I started with, A, but the formal power series of A in one variable, and that you should think, of course, of that one variable as Planck's constant. Right? I've always thought a variable is a constant, right? Yeah, but you do let Planck's constant tend to zero. How a constant can tend to zero, this offends all the rules I was taught in first year analysis. Sorry.
My question about ordering. So this expression using this, we could call Poisson tensor. That's the two vector. Why do you write the two vector on the left and not on the right? I think of a one form and evaluating a one form. Is there a convention there, or what's the?
I'm talking about the pairing between the two of them, and I'm just probably the best way to write it is to put an angle brackets around it, to write brackets P, dF, dg, but I mean that thing. Whether you put it on the right or the left, I'm not sure. Right, so this thing is a product on this algebra, so which is, first of all, it's bilinear over formal power series, and I suppose we're working with real coefficients. So it's bilinear over that. It's associative. and secondly, it's got to equal. It's got to, and the product. So we can write. Let me write it. We can write such a series. A star B, F star, I call them A star B, is equal to sum B n of T, B n of AB, sorry. I've left out a term. Oh no, okay. B n of AB, T to the n. Okay, we can write it out like that. Formal power series, and we require that B naught of AB is just the product AB. Okay, so this product modulo T times R of T is just the product you've started with. So the leading term in this product is just the product AB, and then you can see that it's deformation in the sense when you put T equals 0, you get the product you started off with. So that's what we mean by a star product. Now, associated to the star product, so a formal deformation. Gosh, I'm really kind of tangling with all the bits and pieces here. So a formal deformation quantization of M, of the Poisson manifold M, is a star product on A such that Poisson bracket of A and B is just B1 of AB minus B1 of BA. So one way to think about this is to, if normally in deformation theory, the first term of a deformation like this, the derivative of the deformation at 0, is a tangent vector to the moduli space of deformations. So what I'm saying is that it's a formal deformation quantization of M is sort of like integrating the Poisson bracket in the direction. Integrating the Poisson bracket, thinking of the Poisson bracket as being a vector field. You may think that mumbo jumbo. Precisely what I mean is that.
Excuse me, A and B are power series, right?
Sorry?
What are A and B?
Oh, I beg your pardon. Since it's bilinear over R of T, right? It's sufficient to actually give it on elements A and B are in A, right? I'm using the fact that it's bilinear over R of T to say that all I need to do is characterize this series on elements of the algebra.
To emphasize the deformation aspect, would you label this star operation with a subscript T? With each T, that's the...
Well, I mean, yeah, T is in it, right? T. So you want to write A star B of T.
Or actually star subscript T, actually label the operation.
You might do. I'd prefer not to, if you don't mind. Right? Because it is.
Just you made this identification, so I was going to say star subscript 0 is your trivial product, AB.
Yeah. Well, then I would probably want to. Okay, I could if you want to. Yeah, but I'd prefer not to, if you don't mind.
This is the question of what you're deforming, so in that sense you can interpret it as a deformation of the product operation.
Yeah. This is a deformation of the product operation. Exactly. That's what this thing says, right?
Does this determine a deformation in all dimensions? That is, can I replace A of T by A of T1 TK?
I don't know.
In a natural way, I mean. If you know how to deform in one direction, you can deform in all directions.
I suppose you could, but I haven't really thought about that. I haven't really thought about that, and I don't.
It's called universal deformation.
Yeah, I guess you can, can't you? Yeah, that would be a universal deformation, not a. Yeah. Sorry, of course you can. That's absolutely correct.
And you need to get the dimension of the moduli space by computing the H1, and then it gives you the dimension of H1 gives you the numbers of T and 0.
So there is no obstruction to deforming.
No, I think that's what the theorem says.
Yeah.
That was the theorem I'm
No,
coming
no,
to
I
test.
mean,
Yeah.
deforming more dimensions. Once
Oh,
you
no,
know
no, no,
in one
no.
dimension.
Yeah. All right, now let's see how I can do. Okay, well, I'm at a stage where I can actually state precisely what Kontsevich proves. Every Poisson manifold has a deformation quantization. I've dropped the word formal. I've dropped the word formal out of this now, right? But it is a formal. Let me put that word formal in brackets. Okay. So every Poisson manifold actually has such a formal deformation. Now, how can you approach this problem? Well, the approach, and this is, I think, this, I think, is the idea behind that paper of Bayer and Flato, etc., etc. The idea is to try to apply Gerstenhaber's deformation theory of algebraic structures in this situation. So we use Gerstenhaber's deformation theory. In order to get a handle on this problem. And so let me start with, so we start with some vector space over some field K. And I'll probably generally assume the characteristic of K is 0, but I think most of what I say will only require the characteristic of K to be not equal to. You sometimes want to put a half around somewhere. So we look at the thing which I call CP of VV, by which I just mean linear maps from V tensor P into V. Now this thing has got a rather curious structure. It's got a sort of composition, a circle I composition. So if I'd say what this means. If I've got F in CP of VV and G in CQ of VV, then what I do is I form F circle I. So this is going to be a function of, it's going to be, so S, so well, it'll be in, and the formula for it is this, F circle IG applied to V1 up to Vp plus Q minus 1, is what I do is I take F of V1 up to Vi minus 1, then I apply G to Vi up to V I plus P minus 1. Q, sorry.
I plus Q minus 1.
I plus Q minus 1. Ooh. And then I write down the rests. P plus Q. Okay, so what I'm doing is you should think of this as a line of variables like that. You slot in a G to the segment of length Q starting at I. Okay. Now this is a curious operation. It satisfies the following sort of purely. That's the circle I, and F circle G would be the sum, and there's some signs which I'm not going to try and make explicit. F circle IG. Okay, it's the sum over I of the F circle IG. Now this thing has the following algebraic identity, and I'll write it like this. Suppose I've got F, G, and H. Then what I'm going to write is AF of GH. Well, this is the associator of the triple FGH. So this is F circle G circle H plus minus, sorry. Right? And the identity it satisfies is this, that this thing is symmetric. Right? I write it like that because I want to. I write it like that instead of just writing FGH because I want to point out that F has a special role here. There's a difference between the roles of F, G, and H in this identity. So it follows. It follows that. Oh no! Again. Okay, I'll just. It follows that this is sometimes called a pre-Lie algebra or something like that. It follows that if I take the commutator of the circle operation, and there's a sign here. I'll write minus G circle F, but I should put the correct sign. I think this. Well, I'll write it.
I suppose there's a sign for the equation for the AF already. No?
Sorry.
I suppose there's a sign in the previous equation already.
No, because that involves no swapping of F and G.
Of G and H.
Yes, you swapped G.
Oh, sorry, I beg your pardon. I've got there's a sign there, isn't there? There's a sign there. Sorry. These signs.
As soon as you switch to variables, you have to put a sign.
Yeah, I think one must accept that convention.
Well, if you have
Sorry.
yeah.
If you say A sub F is graded symmetric. you can
Graded
write the
symmetric.
equation.
F is this thing is graded symmetric, right? I'm going to write the signs here: -1 to the and the degree of F, here I'm going to write the degree of F equals P if F is in CP. Okay? So this thing is I'm going to write this graded Lie bracket of degree -1. So it's really, if I shift, what I mean is if I shift all the gradings down by 1, of everything down by 1, then this thing is a graded Lie bracket with that grading. So it satisfies the Jacobi identity. Now it's interesting. Here's an interesting and important example. The example I want to look at is, suppose I've got mu in C2 VV. I think I'm going to write, right? I'm going to force myself to use half the board here. Right? So then I think of mu as a product. So it's a product. It's a bilinear function on V, and you get this nice way of expressing associativity. Mu is associative if and only if mu circle mu, which is true if and only if the bracket of mu equals 0, and there I need the characteristic 2, characteristic not 2, because otherwise I'd have a half there, right? Okay. So this product is associative if and only if mu circle mu is 0. It follows, of course, then that if I define d mu from Cp of VV by d mu of x is the commutator of mu with x right? And again, there are signs involved there. There are signs involved. This should be a plus or minus according to the graded commutator.
You mean
Right.
with circle x minus x plus minus x. So mu
Oh, sorry, beg your
circle
pardon.
x
Yeah, sorry, yeah. Which is the bracket with mu, exactly. Sorry, I beg your pardon, I was getting my... That this thing is a differential. D mu composed d mu. And we get a differential on, so we get a chain complex, C star V V, with, okay, now this is, now of course, this is the Hochschild complex of the associative algebra A, which is just V with the product mu. You may have seen the Hochschild complex before, constructed before in terms of a formula, and if you have, it's good to unpackage what I've written, which is a rather condensed, a neat condensed way of describing the Hochschild complex. It is just the Hochschild boundary operator is just given by commutator in a this Gerstenhaber bracket with x. So the next thing to do is to apply this basic idea to apply this basic idea. Well, after all, we're trying to construct an associative product on some algebra. Right? The algebra is A of t. So I'm going to apply this little bit of general theory to that example. Let me just go and grab some. So construction of deformation quantization. So we apply this to the construction. So our star product is uniquely determined by a map which I'll call theta from A tensor A into A power series on T. Right? It's that point at the beginning that since the star product is bilinear over the formal power series ring, it's uniquely determined by this thing theta. And theta of AB is AB, the product you started off with, plus C of AB. Okay, so I just say that by definition it had to start with the product. C is the rest of it. C is the rest of it, and that is some power series with the constant term 0. Now, what we want is the thing we want is that this is associative, right? What we want is that this thing is associative, so that mu plus c, circle mu plus c, right, where mu is the product. Now write that formula out using the fact that mu composed mu is 0, and you get the so-called Maurer-Cartan equation. D mu of c plus c circle c equals 0. And write that out, and you get this equation, or it's sometimes written d mu of c plus 1/2 c, the bracket of c was c is 0. So this is a thing called the So what we're looking for then is solutions of the Maurer-Cartan equation in this context, right? So we're looking for yeah. So we're looking for solutions of the Maurer-Cartan equation, but in the Hochschild complex of A power series in T. So we're looking for solutions of the Maurer-Cartan equation there. Okay, now the next thing is that, well, look, this is the Hochschild complex. There's a complex, there's a boundary operator here. We're looking for solutions in the Hochschild complex. Well, the first obstruction to finding a solution in the Hochschild complex is to find a solution in the cohomology of the Hochschild complex. So, are there solutions in the Hochschild homology? Well, I'll write this as the cohomology of this complex CAA power series in T, with respect, of course, to the boundary operator, which depends on defined by the product. Now remember what A is. A is smooth functions on M. Okay. Now there's a basic thing.
You need to say something here, because on your Hochschild complex, actually, what you didn't say is that d mu is a derivation with the bracket we had before. So Hochschild complex of DG algebra, and then you pass to the homology, and you consider the induced bracket in second.
Yeah. I've got to say what I've got to say. Of course, what Bruno is pointing out is what I've got to say is this actually is a Lie algebra, right? That the d mu is a derivation. The d mu is a derivation of the bracket, right? So don't write that down. So this is graded Lie algebra. Since d mu is a derivation of the bracket. Okay, right. So this thing is a graded Lie algebra. So I look for solutions of the Maurer-Cartan equation in this in the cohomology. Are there any obstructions in cohomologies? The question I'm asking is that are there any obstructions to the existence of this C in the cohomology? Now here again we come across another beautiful theorem. This is the Hochschild-Constant-Rosenberg theorem. And what this thing does is tell us what the Hochschild cohomology of smooth functions are.
On the second one, why is there a star on the second one? You want to take 2 elements a day and get.
That's a placeholder, right? In whichever degree it is.
I don't understand why. I'm confused. Why is it not 2?
It is 2, but I'm just writing C star of AA for the whole thing, right? Right, I'm writing C star of A. That means an element in degree 2 of that thing satisfying the Maurer-Cartan equation. So it's just sloppy notation, right? So the Hochschild-Constant-Rosenberg theorem tells us what the Hochschild cohomology is. So what the Hochschild-Constant-Rosenberg theorem tells us that the Hochschild homology in degree P of C infinity M, I'll write A is C infinity M, is just the same as the sections over M of the pth exterior power of the tangent bundle of M. Okay? So this is a classical computation. You have to be careful here, by the way. Because I'm dealing with the algebra A is smooth functions on M, so it's an infinite dimensional algebra. So what I should really use is the sort of the differentiable cochains Cp of C infinity M should be interpreted as Hom from the smooth functions on M to the P into m, into smooth functions into C infinity m, and I have to put a diff down there. I'd have to put a diff down there. These functions have to be differential operators, multi-differential operators. That is, if you hold all but one of the variables fixed, the function you have there is a differential operator in the remaining variable. Okay? So that's a technical thing which I thought I should tell you about, just you know, just to point out that there is a technical point here.
And in this technical point, if you compute the cohomology, will it be the same as the Hofschild cohomology?
Say again?
So if you take just the Hofschild...
If you remove the diff,
yes, just take the Hofschild cochains without the...
without any completions.
Yeah, exactly.
Yeah, you won't get the right answer.
So the Hofschild cohomology will, the actual Hofschild cohomology will be the wrong answer. So
Yeah,
you have to
yeah.
take this simply into
Yeah,
account.
you'll get. I think you will, however, get a dense subalgebra of this. Right. You know, we're dealing with infinite dimensional things, right? So you know the kind of complications you're going to get if you don't specify, right? You see, another one is, you know, we're talking. You know, this is the whole theory of completed tensor products, right? Right. You know, you have to worry about that kind of thing. But I think you certainly don't get it if you just use the ordinary definition.
In the sense of the grandfather of grandfather.
Absolutely. So, okay, so the Hofschild cohomology is this space of polyvector fields. Now, what? No, I don't think so. No. I don't think that needs to be compact for this theorem. It's certainly true for Rn, for example. Right, so no, I don't think M needs to be compact. Now, what about the various structures we've seen? Now, the Poisson bracket here, which is an element in HH2, right? What does this thing go to? This thing goes to the Poisson tensor. Remember that my manifold has a Poisson bracket. Sorry. I think I've left out. Okay. So under this isomorphism, the Poisson bracket corresponds to the Poisson. The Poisson bracket goes over to the Poisson tensor. I said this was, you know, I mentioned what this Poisson tensor was. And the Gerstenhaber bracket, this thing then, which is the Gerstenhaber bracket, which is the bracket in Hofschild homology, right? The bracket in Hofschild homology goes over to a thing called the Schouten bracket. Now, what is this Schouten bracket?
Excuse me, I have still a question about the HPR theorem. Does M have to be connected? So if you have, say, R and R2, two connected components, then the polyvector fields will be separated, but you might have...
Yeah, okay. Yeah, I'll make M connected. I'll definitely make M connected. Right. I mean, because if it's disconnected, what you mean is the thing for each component separately, and whether when you put it right, that which is exactly the point. Now, one nice thing which happens here is that there is a solution to these equations. So classical computation tells us that the
Could you explain what you mean by brackets G maps to bracket M?
the bracket G is the bracket in Hofschild homology, which we came up here. I haven't told you what the Schouten bracket is, and that's what we're going to do. Right. The Schouten bracket is determined by the following set of...
You have talked about it later.
Pardon?
When you wrote this is a gradient algebra.
That's
No.
That's with the Gerstenhaber bracket.
No, but it was under homology, and so I guess it's what's on the right, no?
Sorry?
Well, the graded algebra is under homology, no?
Yeah, but what I'm trying to say is, yeah, it is a bracket in homology, yeah, absolutely. But it's something else as well. Right. So this bracket S is the so-called Schouten bracket.
Is there a particular reason why you wrote your rule from left to right?
Pardon?
I'm sorry, it's just maybe because it's confusing for people. Your rows should go left and right. I mean, it's under this isomorphism.
Yeah.
Poisson correspond to and Schouten.
Yeah.
Orientation.
Right. So what properties does the Schouten bracket have? Well, first of all, if xi and eta are vector fields, then the bracket of xi and eta, the Schouten bracket, is just the ordinary Lie bracket. That's the first property this thing has, that on vector fields, it's just the Lie bracket of vector fields. And the second property it has is that there's an obvious product in these things, that the bracket of alpha, beta, wedge, gamma, right, there's an obvious, if I've got a section of the pth exterior power of the tangent bundle and a section of the qth exterior power, I can take their exterior product and get something like p plus q. And this thing is a derivation, a graded derivation. And then, of course, the usual sign convention. And that then uniquely determines it, of course, because I've determined it on enough things so that it's complete. So, for example, if I want to work out xi, a vector field bracketed with beta, wedge, gamma, I use this thing. Right? And that completely determines the bracket. Because locally, everything is given by wedges. And it's a classical computation that the Schouten bracket of the Poisson tensor is 0. Now, the Gerstenhaber bracket of the corresponding object over here is not 0.
Down.
This one is C2, right? Right? The Gerstenhaber bracket of the Poisson bracket, considered as the Hochschild 2 cochain, is not 0. Right? But when you move over into homology, when you move over to the polyvector fields, the Schouten bracket of the Poisson tensor is 0.
Equation down. In the homology, d mu c will disappear in the homology.
That's right. So d mu. So in the Hochschild cohomology, I forgot what my notation now, of AA, we have these equations DC.
DC 0.
Yeah, sorry, that's right. I should be saying.
CC 0.
C, yeah, C.
Bracket C.
D mu of P goes to 0, right? And P, Schouten bracket P, is 0. So, with power series in T. So we have a solution there. We can take the solution is just this thing is 0, and the P Scouten bracket with P is 0. So we have a solution at the level of cohomology. So I say it again because this is really, well, of course everyone knew that. I mean, this was known maybe even to people, the originators of the theory, that you have no obstruction in cohomology, otherwise they wouldn't have gone on. But now Kontsevich comes into the picture.
Should also say that the PP0 is a characterization of the Poisson bracket.
Yeah.
Of the Poisson tensor.
Of a Poisson tensor, yeah. A Poisson tensor must have that property. So this is where Kontsevich steps in. Well, the first thing Kontsevich said, well, I need to tell you what the definition of a quasi-isomorphism. So suppose I've got L1, L2, and these are differential graded Lie algebras. So they have a differential, they have a boundary map, they have a Lie bracket, a graded Lie bracket. So there are signs, and the D map is a derivation of the Lie bracket. Okay. So L1, a quasi-isomorphism is a map of differential graded Lie algebras, which is an isomorphism in homology. Okay, so that's what a quasi-isomorphism. It's got to be a map of differential graded algebras, so it has to respect the differential in the Lie bracket, and it has to be an isomorphism in homology. No one tells you that the inverse of that isomorphism is given by a map of Lie algebras, but nonetheless you can say L1 and L2 are quasi-isomorphic if there exists I call it M and quasi-isomorphisms So there's a thing M up here, and it's quasi-isomorphic to L. There's a quasi-isomorphism to L1, and there's a quasi-isomorphism to L2. It's not obvious that that's an equivalence relation, but it is an equivalence relation. Right? It's not very difficult to prove it's an equivalence relation, and it's not very difficult to prove it's the equivalence relation generated by the relation there is a quasi-isomorphism from L1 into L2. So you make that into an equivalence relation in the most obvious way. Now what Kontsevich says is, first of all, that actually the problem we're talking about is actually invariant under quasi-isomorphisms. That is, if L1 and L2 then there is a solution to the Maurer-Cartan equation in L1 if and only if there is a solution. Right? So the problem of the existence of a solution to the Maurer-Cartan equation is a homotopy invariant of differential graded Lie algebras. That's not very difficult to prove, by the way. In fact, something much stronger is true, but I don't really need that, or, well, we will need that at some time. The stronger thing is that, in fact, if L1 and L2 are quasi-isomorphic, then there's a bijection between the equivalence classes of solutions of the Maurer-Cartan equation in L1 and the equivalence classes of solutions of the equation Maurer-Cartan in L2. So the space of solutions of the Maurer-Cartan equations modulo equivalence is a homotopy invariant of the differential graded Lie algebra. Okay? The second thing Kontsevich shows, well, Kontsevich's formality theorem tells us that, in fact, the Hochschild cohomology, sorry, the two things that is quasi-isomorphic to the Hochschild homology of A with coefficients in T. So A here, of course, A is C infinity M. So actually, you've actually solved the problem. So of course, since there's a solution in here, since there's a solution to the Maurer-Cartan equation in here, there's a solution to the Maurer-Cartan equation in there. Therefore, there is a deformation. Therefore, there is a formal deformation of the Poisson manifold. Okay? So let's say again, there's a solution to the Maurer-Cartan equation in there. Therefore, there's a solution to the Maurer-Cartan equation in there. Therefore, there exists a deformation quantization. And it's kind of, I actually think that's a big step to take. Right? Even to think that maybe you have to think in a particular way, right? In order to go from, in order to think of using the ideas of homotopy theory, really, quasi-isomorphism, in order to solve that problem.
Excuse me, this formality theorem, is it true from any manifold or only for n?
It's true for any Poisson manifold. And
so
the way
we have formality theorem, not just gluing of the solutions.
Pardon? No, you mean, but yeah, gluing the solutions is the way you do it. Yes.
So
you solve it first on Rn, and then you patch solutions together on globally on a manifold.
Yeah, but does it then imply that there is formality theorem globally, or just that there is a projection between the classes of solutions? I mean,
I see your question. I believe the formality theorem is valid for a general manifold.
I remember that the Koncevich paper itself was only for Rn. Maybe later it was proved.
No, he did it for all M, Kontsevich, yeah.
No, there were many attempts before.
There
But
were huge numbers of attempts. Oh, this generated a vast literature.
but the final solution was Kontsevich.
Yeah.
And everything was contained.
Yes, everything is contained in Kontsevich's solution. Okay, so, well, I've got to the end of this statement of the discussion of deformation quantization, but I want to say, and I haven't actually left myself very much time, where we go from here. But so let me just say a couple of things about where we go from here, right? Because I think not only did Kontsevich's work draw on a lot of things, right? It opened up a lot of things as well. And that's one of the important points about it. And I want to try and tell you something about what those things are. But before that, I need to say something about the so-called Deligne conjecture. One of the things which always amuses me about mathematics and mathematicians is that if a Fields medalist makes a conjecture, when it's proved, it's known as the Deligne conjecture. Whereas if Jim McClure and Jeff Smith, it's called the Deligne conjecture, not the McClure-Smith theorem. Anyway, that's life. I'm not going to try and... And this Deligne conjecture is, well, what exactly is the full structure of the Hochschild complex? Right? I've shown you the Hochschild complex C star of AA with its differential D, which defined by the multiplication. I've shown you the Gerstenhaber bracket, but it's got more structure. There's a cup product. So remember, if I've got F from A tensor P into A, and G from A tensor Q into A, then the cup product of these, F cup G, is something I can define on P plus Q variables and it's given by f of the first p, g of the remaining ones. I follow the convention which I learned in Lode and Quillen's paper of writing a comma instead of a tensor sign. So that's the cup product. Pardon?
Mu also is there somehow.
No,
You here, you multiply the result of f.
mu is what multiplies f by g.
Yes.
Pardon?
The product.
Oh, I see. You want me to put mu? Yeah, okay. This is the product of f and g. Mu of mu. Yeah. Sorry.
It should be mu of f and g.
Yeah. Okay. And this thing, the differential is a derivation of this as well. And again, there's a sign f. So in this Hochschild complex, we've got D, we've got brackets, and we've got the cup product. We've got the bracket and the cup product. What structure is there? What's the structural relations really between this and this? D is a derivation of this, D is a derivation of that. And the Deligne conjecture gives you an answer to this.
That's why we need higher.
I know. So, well, first of all, at the level of cohomology, we have the following relations. Well, that is a graded Lie bracket. Of degree minus is graded commutative. We have the Jacobi identity. For the bracket. And it remains, of course, to give the formula for the bracket on the product. And I'll write it like this. Bracket of A, B, cap C.
A, B, cap C.
Yeah. Plus or minus A, C, cap B. Okay, it's the bracket. The bracket is a derivation of the bracket. That's the Jacobi identity, and the bracket is the derivation of the product, and that's that's a souped-up version. That's a graded version of the Poisson identity.
And there, the cut was the wedge that you had before, no? So it satisfies these equations, and under the isomorphism of the Hochschild cohomology of smooth functions, this indeed corresponds to the wedge product in the polyvector fields. So there's such a thing is usually called a Gerstenhaber algebra. And actually, I remember explaining this in a talk in Sheffield. And Kirill Mackenzie, who was a symplectic geometer, was there. And he said, well, don't you mean the Poisson algebra? The Gerstenhaber algebra? The algebra of smooth functions on M is just the sections over M of, I'll write it, I just write a lambda T of M, the exterior algebra of Tm. And in this, the bracket is the Schouten bracket, the product is the wedge product. What else? Well, that's all I need to say, right? And this thing, Kirill Mackenzie regards the symplectic geometers regard as the Gerstenhaber algebra, the only example anyone with any sense would look at. Right. So in cohomology, we have these nice relations. Now, a little elementary thought tells you do not have these relations in the Hochschild complex itself, right? They're only true modulo boundaries. So So, so this is, I say, proved by McClure-Smith, Voronov, Sasha Voronov, and I think Kontsevich. And I'm not putting them in anything like historical order, but it's got a proof. So have I let someone out?
We improved it with Zoe-Bollmann, so maybe it's fair.
Oh, thank you. Sorry. Yeah. I mean, maybe there's another long list of names. Long list of names there. I'd like to put my name there, but unfortunately, Ezra and I, the work we did was wrong. It's very interesting to look at, by the way, to Google the Deligne conjecture. Well, first of all, you get a long list, right, and then you find the right one. And it says that this has been proved now, despite no one disputes it's been proved now. After some rather shaky beginnings, something of that kind. And I'm afraid Ezra Getzer and I are the one responsible for the shaky beginnings. I think, for the shady side of the subject.
What is the statement?
Sorry. Right. Well, of course, again, I'm not going to tell you. I'm not. But so, C star AA is a G-infinity algebra, so which is a Gerstenhaber algebra up to coherent homotopies. And I'm not going to try and tell you what up to coherent homotopies mean, because it's there. So that's the point where you need the theory of operads. Right? That's it. To make precise what you mean by up to coherent homotopies is exactly the role of the theory of operads in this game. Okay. Now, I'm going to say a couple more things. So this brings in braid groups. This actually implies something about braid groups. Braid groups, double loop spaces, spaces like loops 2 of x. This brings in quite naturally braid groups, because technically the operad for double loop spaces involves spaces which are the homotopy type of the classifying space of the pure braid group. So this immediately brings in braid groups, and therefore it puts it somewhere in the same region as the Grothendieck-Teichmuller group, which is the automorphism, which is a group of automorphisms, the profinite completion of the braid groups. So somehow or other, there is a path, right, from this part of the world to that part of the world. What I'm talking about lives in this part of the world, and the Grothendieck-Teichmuller groups live in another this part of the world. But there is a link between them. The second thing I want to say is that it's double loop spaces. And there's not really time to explain this, but I do want to say, so in the world of topology, what double loop space am I talking about? The context here is that I defined Hochschild homology for algebras. I could define Hochschild homology for differential graded algebras. I could then specialize that differential graded algebra to be the algebra of cochains on a topological space. And that would say, then the Deligne conjecture would say you've got this G-infinity structure on that. Topologically, G-infinity structures correspond to double loop spaces. So what double loop space is it? And I claim the relevant double loop space, the cochains on X, a topological space, then the double loop space we're looking at is the loops on the space of homotopy equivalences of X. Okay? Why is this a double loop space? Well, this thing is a group. Therefore, it's a loop space. It's loops on its classifying space.
Sorry, what is AG?
the homotopy equivalences, the group of homotopy equivalences of X. Okay? The group of homotopy equivalences of X. So again, there's another one of these sort of crazy squiggly arrows which relates these two in some way or other. So we've gone in another direction as well. Somehow or other, the study of this space, the space of homotopy equivalences, or at least its loop space, is somehow or other related to Hochschild cohomology, the Hochschild cohomology of cochains. Well, I think I've already used up too much of my time, so I'll stop there. Thank you.
But we have time for questions.
Yeah.
Always. We always have time for questions. So is there any question?
In the statement of Konsevich's theorem, you got rid of the T. You ask it.
That's me being. So it's valid.
Is there an example where it's not equivalent, where C star of AA is not equivalent to H star of AA?
I think the two questions are equivalent.
So, so you think C star of AA is always equivalent
Oh,
to H
I mean,
star?
in the example we're talking about.
I was wondering if you had a Poisson manifold M,
Yeah.
such that C star of AA is not equivalent, quasi-isomorphic. Sorry, it's not.
No. Konsevich's theorem is if you have a Poisson manifold, then C star of AA
So
is.
without the T. So when you construct some sort of chain of quasi-isomorphisms between.
Oh, I see what
you
you're
don't
saying.
need
If
that extra
Konsevich uses C star of AA is quasi-isomorphic too, and therefore deduces that when you put the power series, it's quasi-isomorphic too. So your question is there an example where they're quasi-isomorphic with power series, but not quasi-isomorphic without the power series?
I didn't realize Konsevich had proven.
Okay,
without
sorry.
the power
Yeah,
series.
okay.